Hi everyone, my name is Tristan Sylvain and I'll be presenting object-centric image generation from layouts. First of all, I'll talk about the motivations for this work. The first motivation was to generate realistic scenes with well-defined objects. On the left-hand side, you can see outputs of our model and different baselines with fixed layouts. As you can see, in many cases, while the model will generate an image that looks quite well overall, sometimes individual objects or parts of the scene do not look correct. Sometimes, for example, as you can see for the animals on row D, you have a scenery that looks quite okay, but the animals themselves are merged or blurry or not defined. Also, sometimes the objects themselves are not completely well defined, especially if they occupy a small area. To illustrate this point, we started with donuts on the edges of each layout, and we made them gradually converge to the center. As you can see, our method maintains separate donuts, whereas most of the other baselines tend to form a garbled image at the center, which does not really represent what a donut should be. This was our first motivation. Our second motivation was generated scenes that actually correctly matched the layout. So to illustrate this, another figure taken from the paper. As you can see, for the baselines we're looking at, they often generate realistic scenes here, but scenes that don't actually match the input layout. As you can see, there are many more people in both cases than there are supposed to be given the layout. Common issues which lead to what we call low layout fidelity. You might have spurious or missing objects, you might have merged objects, or you might have objects that are unidentifiable. So this is also a major issue. Now I'll talk briefly about the components of our approach. First of all, we use a scene graph similarity module. This is a retrieval-based module that encourages the generated scene to closely match the input layout. This works by essentially taking the layout, turning it into a scene graph, using a GCN to embed it, and then applying global loss with respect to global and local image features. This SGSM module, by the fact that it acts as a retrieval-based module, strongly encourages the generated scenes to correctly match the input layout. Here is the full architecture diagram. I'll go over some of the components briefly. As you can see, we have layout, which is fed as a condition to the batch norm. Layout is also used to generate a scene graph, which is then fed to a GCN, which will allow us to compute the SGSM. In addition to this, we use a perceptual loss and an instance prior, which is simply taking the bounding box to generate contours, which are actually the contours of the bounding boxes of each object. This helps object quality a little bit. Now, I'll talk briefly about the results. First of all, quantitative results. We used the classical inception score, FID, and classifier accuracy score that are commonly used in the literature. And as you can see, we generate a large improvement over the baselines for each of these metrics. These are results in 128 by 128, but results in 64 by 64 are similar. So overall, we improve on the baselines a lot. In particular, CES scores are strongly improved, which is an indication of the fact that we're generating very realistic objects according to this metric. Qualitative results. So as you can see here, these are generated images that are taken at random. And while many of the baselines introduce spurious objects, overall, we tend to match the input layout very well. And this has been confirmed by manual evaluation by many researchers at random. So the user study confirms what I was saying. People judge our images to have significantly higher layout fidelity. So thank you for listening to this presentation. Please reach out to me if you have any questions about this work. Our workshop paper is hosted on the workshop website, and in addition, you can find the full paper at archive on the given link. Thank you.
Hello everyone, my name is Yu Chuan. I'm working at PAI Labs. Today I'm going to talk about our research work named Segmentation, text-to-image generation with segmentation attention. So the task of text-to-image synthesis is central to many applications. A lot of research use generative models to achieve satisfactory visual quality. However, these models would frequently generate objects with deformed shapes or unrealistic layouts. To solve this problem, we designed Segmentation, which utilizes segmentation information to add spatial attention. We hope that the spatial attention would regulate the layout of generated images. An experiment has shown promising results. A GAN is one of the state-of-the-art text-to-image GAN model. This GAN is conditioned on text input rather than noise. The model used cost-to-fan strategy for the GAN training to get better image quality. Also, this model is conditioned on both sentence level and word level features. So based on a Tangan work, we proposed a model that takes text description as well as segmentation mask as input. This model used segmentation to do the spatial attention after each upsample layer in generator. We also proposed a self-attention strategy. We use cost-to-find architecture for the better image results. Other parts like text encoder, word features, and sentence features are inherited from the Tangan model. Now we introduce the details of segmentation attention module. When giving a segmentation mask, we pass it to a couple of convolutional layers to produce the segmentation features. Then we do the element-wise multiplication and addition to the previous layer of the image features. This method is related to many work like Spade or Eden. For self-attention, we will train another generator for the segmentation mask, and the model can use generated segmentation to do the spatial constraint. This method avoids using the real segmentation data during the inference phase. In generative adversarial network, the classic objective function is a min-maxing between the generator and discriminator. Our model basically is a GAN, which generator is conditioned on text description as well as segmentation, and the discriminator is conditioned on the text description. And our total loss is consist of image generator loss, segmentation generator loss, and text image matching loss, which is introduced in a Tangan. We use 2 datasets and 2 quantitative measurements to evaluate our model. Inception score has been widely used to evaluate the quality of generated images, and our precision score is a method to determine whether the generated images is well conditioned on the given text description. Our model achieves highest inception scores on both CUB and Oxford datasets, and our self-attention model also gets a pretty good inception score. We applied our segmentation attention module on StackGAN and get better inception scores. This indicates that our model can help constrain the training of different GAN models. As shown in this figure, compared to the baseline model, our model can generate results with better object shapes. Although self-attention model use fixed segmentation, it is able to constrain the object shapes and generate better images than the baseline model. This figure shows image samples comparing to the segmentation mask. We can know that in our model, the segmentation provides very good control on the object shapes. Thank you for listening.
Hello, I am Junbom Cha from Naver Clover AI Research. I'll introduce our work toward high-quality feature font generation with dual memory. Here, we aim to generate a high-quality font library with only a few style samples. There exist some prior works for the feature font generation task, but they often fail to capture detailed styles as shown in this figure. In this work, we solve the problem by exploring the characteristics of scripts' compositionality. We focus on a famous family of scripts called compositional scripts, which are composed of a combination of subglyphs or components. For example, every Korean letter can be decomposed into 3 components. Here, we focus on the Korean scripts only, but our method is applicable to the most of compositional scripts. Also, the most of compositional scripts have glyph-rich property. For example, Chinese script has more than 50,000 glyphs, and Korean script has 11,172 glyphs. Therefore, we need an automatic font generation method for the compositional scripts. This is the conceptual architecture of our model. The model is composed of encoder, decoder, and memory. Given reference style glyphs are encoded to the component-wise features by encoder. During training, the encoder learns how to decompose the glyphs to the components. The encoded features are written to the dynamic memory. In the conceptual figure, the encoded feature can be directly fed to the decoder without the memory. But in the test scenario, the target glyph is unknown in the reference style glyphs, so we need the dynamic memory to connect the encoder with the decoder. The decoder loads features from the memory and synthesizes the target glyphs. During training, decoder learns how to combine the component-wise features. Finally, we introduce one more module, persistent memory. It is learned embedding, which learns the global composition information and the intrinsic shape of each component. This memory is trained independent to the font style. This is the full architecture of dual memory font generation network. The generation process is composed of encoding and decoding stages. In the encoding stage, the reference style glyphs are encoded to the component features and stored into the dynamic memory. After the encoder fills up the memory, the decoder fetches the component features from the memories and synthesizes the target glyph. Let's see the experimental results. This is the visual comparison on the Korean handwriting dataset. Previous methods generate the contents of glyphs and capture global styles well, but the detailed local styles look different from the ground truth. For better comparison, we highlight the sum of detailed local styles in the last row. To quantitatively evaluate the model more closely to the human perception, we train content classifier and style classifier. Using the classifiers, we measure the classification accuracy and MFID of the synthesized glyphs. As shown in the table, DM font scores the best in all measures. AGSNet shows similar results in the content score, but our model dominates the stylization performance. We also conduct the user study using the real handwriting glyphs. This dataset is more unrefined and noisy than validation dataset. In the user study, we investigate the content, style, and overall preference. Similar to the quantitative evaluation results, AGSNet and DM fonts are comparable in the content evaluation, and our method is dominant in the style preference. To sum up, we proposed a novel feature font generation model, and it improves the generation quality remarkably, especially in the detailed stylization. In this presentation, we omit and abstract a lot of details of our work, so please check our paper for the details. In addition to the workshop paper, recently we released the extended version to the archive. Thank you for your attention.
Hi, I'm Sang Mo from KITE, and I'll introduce our work FreezeD for fine-tuning Ganz. Modern Ganz show remarkable success in image generation, but they require lots of training data and computational resources. Several works propose a transfer learning approach, but they are often prone to overfitting or limited to learning small distribution shifts. We find that simply freezing the lower layers of the discriminator while fine-tuning Ganz the project layer performs the prior method. In particular, FreezeD shows more stable and better result than the vanilla fine-tuning. FreezeD consistently outperforms fine-tuning under various datasets. Also, FreezeD generates more less consistent samples. We compare FreezeD with various prior methods and do an ablation study on freezing layers. We hope FreezeD set a proper baseline for future researches on transfer learning with Ganz. Please check our paper for more details. Thanks.
In this work, we present mix and match, which disentangles, encodes, and combines background, shape, texture, and pose from real images to generate a new image. Our model does this without any mask or label annotations. Our model consists of 4 encoders to disentangle and encode different factors from real images, and a fine-grained generator to generate new images conditioned on the latent codes. We use adversarial learning to match the paired image code distributions between the encoder and the generator. With mix and match, we can colorize cartoons or sketch images where we take the background and foreground color from different real images. We can also animate an object by taking the pose from a reference video clip. Our code and web demo are available on the GitHub link.
This work, we propose interface scan. With interface scan, we can interpret the face semantics learned by Ganz, disentangle various semantics, and further reuse these semantics for face editing. Interface scan consists of 3 steps. Step 1. Synthesize images with randomly sampled latent codes. Step 2. Assign semantic labels to synthesize the images, like male versus female. Step 3. Train a linear boundary in the latent space by using semantic labels as ground truths. By moving latent codes towards the boundary, we can achieve semantic face editing. With interface scan, we can edit facial attributes, vary the face pose, or even fix the artifacts generated by Ganz. We also propose a technique to disentangle different semantics, which we call conditional manipulation. With conditional manipulation, we manage to only change the wanted attribute without affecting the other.
Hello everyone, I will introduce our semantic hierarchy emerges in deep generative representations for scene synthesis. In this work, we propose an effective framework, termed as Huygens, to interpret the semantics learned for scene synthesis. Our framework consists of 3 steps. The first one is to build the image and semantic spaces via the generative models and off-the-shelf classifiers. The boundaries of semantics are identified by probing in the latent space. Finally, verification allows to quantify the causality between activations and semantics. It turns out that generative models which employ layer-wise latent codes could encode semantics from different abstraction levels in a hierarchical manner. Specifically, the bottom layers tend to determine the spatial layout, the lower layers control the categorical objects, the later layers finally render the scene attributes as well as the color scheme. Identifying such variation factors enables semantic scene manipulation. Thanks for.
We propose image to style Ganz++. Here we show some of the applications of our framework. The first one is image painting. The algorithm is able to fill photorealistic details to the defective area. We also show different solutions generated by our algorithm. Here we show our method outperforms other methods across all the metrics. Next, we show local edits using scribbles. Here a scribbled image is converted into semantically meaningful edit of high perceptual quality. We are able to perform various local edits to different images. Face manipulation is yet another application of image to style Ganz++. Here we do attribute level feature transfer from one image to another according to the copy mask. Here the beds are modified according to the attribute image. Thank you for watching.
In this video, we present Sean, a simple but effective building block that enables per-region style control for Ganz conditioned on segmentation masks. Image-to-image translation is an umbrella concept that can be used to describe many problems in computer vision and computer graphics. Among them, semantic image synthesis is particularly useful as it enables easy user control by modifying the input semantic layout image. To date, the best architecture is SPADE. In a nutshell, SPADE synthesizes an image by two inputs. First, a style code extracted by an image encoder or sampled from a noise distribution. Second, a segmentation mask that is used to modulate the scales and biases of the generator activations. However, by analyzing SPADE results, we found two shortcomings that we would like to improve upon. First, SPADE uses only one style code to control the entire style of an image, which is not sufficient for high-quality synthesis or detailed control. Second, inserting style information only in the beginning of a network is not a good architecture choice. Correspondingly, we propose two modifications on SPADE. First, use one style code per region rather than one style code per image. Second, inject style information at multiple locations in the architecture instead of only at the beginning. To implement these ideas, we propose Sean, a normalization layer that modulates the scales and biases of the generator activations by both the per-region style code matrix ST and segmentation mask M. In more detail, the style code matrix ST undergoes a per-style convolution, and the style codes are then broadcast to their corresponding regions according to M to yield a style map. Both the style map and segmentation mask will be passed through separate convolutional layers to generate the modulation parameters. We model the network training as reconstructing the input image by its corresponding segmentation mask and the extracted per-region style codes. During inference, our model allows highly flexible image synthesis by using an arbitrary segmentation mask and selecting separate style codes for each semantic region. Here is an example of our face image editing results. By controlling the style code of the corresponding semantic regions, we can edit the hair, mouth and eyes, skin tone, and background of the input image, respectively. Compared with SPADE, our method is better suited to encode, transfer, and synthesize style in terms of reconstruction quality, variability, and visual quality. Now we show a sequence of style interpolation results with fixed layouts. Finally, we will introduce our user interface for face editing. To the left, we show the current style image from which we extract per-region style codes. In the middle, we show the current segmentation mask. To the right, we show the current result. Here, we show editing results, where all style codes are obtained from a single style image. Note how our method can capture the essence of elements such as hairstyle, skin tone, background, and eyes in a per-region style code and transfer it to a face segmentation mask with very different region shapes. The following is an editing sequence where style codes are selected from different images. For example, we can change the hairstyle, the eyes, the mouth, background, and clothing. We can also modify the final result by painting changes to the segmentation mask. For example, we can extend the hair region to the right, and then paint hair bangs on the forehead. Our code is available on GitHub. Thank you for your attention.